All right, ladies and gentlemen. So I just got a quick video over here for section 9.1. This is the first day out of the chapter 9, out of the quadratics chapter. Hopefully everything's going good on this Wednesday. So I'm going to make some quick notes, and you're going to take these notes. And on tomorrow, just as a reminder, tomorrow I will not be here as well. You'll have another video over section 9.2, and I'm going to give you both homework assignments over section 9.1 and 9.2, and I will go over them on Friday. So again, today you watch a 9.1 video. Tomorrow is the 9.2 video, and then on Friday we will review both 9.1 and 9.2, and we will go over both 9.1 and 9.2 homework. Those will be due on Friday. Okay, I'm going to give you both. I'm going to open it up for both videos right now, and then so you can watch both of them if you want, and then I'll have both homework assignments posted as well. So let's get into it. Okay, so section 9.1, identifying quadratic functions. Now, here's our formal definition of a quadratic function. Go ahead and write this down. Remember, you should be writing down everything that I box here. I will be checking notes on Friday as well. Everything that I tell you to write down, write down. Every example that I do, you must do. So, quadratic function. A quadratic function is a new type of equation that makes a curve. You know, we've looked at straight line equations, but now we're looking at ones that make a curve. We've spent a long time, chapters 7 and 8, multiplying and dividing these polynomials. Okay, one specific type of polynomial is a quadratic. Now, we've seen that word before. That quadratic just means with a degree of 2. We've talked about that before. So any function that has a degree of 2 is considered quadratic. It's not linear. It's got a curve to it. This function is called quadratic. Quadratic function is any function that can be written in standard form, ax squared plus bx plus c. I'm going to emphasize that. That is called standard form, right? We know that form. It has to be in that form when we work with it. A, b, and c are just the a is the number out front, b is the number in the middle, c is the constant. Okay? So let's take a look here. This is, oops, get out of there. This is just the graph of y is equal to x squared. Like, think about a table. If I were to make y is equal to x squared, -2, -1, 0, 1, 2. Think about what's happening when you say x squared. -2 squared, +4. -1 squared, +1. 0 squared, 0. 1 squared, 1. 2 squared, +4. Look at the symmetry here. Look at the symmetry in the y values. Do you see the symmetry in the graph as well? So we've got -1, +1, -2, +4, +1, +1, +2, +4. We see the symmetry with the points. And we have this rounding out point at the bottom. Every quadratic is going to have that. Now, we may move them around the graph, shift them up, down, left, right, reflect them if we wanted to. But basically, that shape is going to stay the same. Now, take a look here on a table. In lesson 5.1, we identified linear functions by finding a constant rate of change. Now, in quadratics, there's going to be a constant change in the second differences. Please, oops, get out of here. Please draw this diagram in your notes. Okay, I want to see that diagram in your notes. So pause here and draw that diagram with the second differences, the first differences, and the constant change. So give you a minute and pause. Now, the second differences basically means that, take a look here. I have a change of 1, I have a change of 3, a change of 5, change of 7. Now, if this were linear, those would all be constant, just like the x values, change 1, 1, 1, 1. But for a quadratic, look at the differences within the differences. It goes up 2, up 2, up 2. So notice that I have a constant, what's called second difference. That's what we're looking at there. If you see that, then it's quadratic. Okay. Now, let's take a look. Let's see. Is this quadratic? Well, let's take a look at our y values. Now, notice first, constant change in x. Good. We don't even really need to check that just to make sure it's a constant change. So let's see. How much are we going from -9 to +2? We went up 7, up 3. Oops, sorry, that's a 1. Up 1, up 7. So take a look at the second differences now. Down 6, down 0, down 6. So are these going to be, is this going to be quadratic? My answer is no, not quadratic. Why? Because we had a difference of 7, difference of 1, difference of 1, difference of 7, which means in the second difference is down 6, down 0, down 6. That's a bummer. No, they have to all be constant. This must be the same for that to be true. Try this one on your own. Remember, every example we do on the board, you do in your notes. Down 3, down 1, up 1, up 3. See the symmetry going on? Is that quadratic? Let's check. Up 2, up 2, up 2. Hey, look at that. We can say it's quadratic. That's my answer. Yes, it is quadratic. Okay, the constant ratio, or sorry, the constant change, because it does say explain why. The constant change in my second differences is a 2. Try one more of those. Oh, geez. Get out of here. Get. Oh. Whoa. Oh, okay. So sorry. I was mistaken. It's not looking at the table now. It's looking at an equation. How do we tell whether it's an equation if it's quadratic or not? Well, do you see an x squared any in there? Look at the degree of that function. Is it a 2? No, it's a 1. So that's not quadratic. It's actually linear. Is that quadratic? Yes, quadratic. Okay. So in an equation, if you see an x squared term, and if it's the highest power, you're looking at the biggest degree, highest power of x is 2, then yes, it is a quadratic. Okay, so let's take a look here. Now, go ahead and write this down. The graph is called a parabola. A parabola. To graph a quadratic function, you generate both ordered pairs to see the shape of the parabola. That curve that we look at is called a parabola. You'll hear me say that word a lot. Okay, it's a smooth curve. Geez, what the heck is going on? All right, so here's what we're going to do. Do this with me. We're going to have a table of values, and we're going to graph this function. Okay, so here's my table of values. What do we always do? -2, -1, 0, 1, 2. Let's see what happens. If I plug in -2, I get -2 squared plus 2. Now, make sure that you plug that in your calculator with those parentheses, because if you don't, it's going to come out wrong. It's a +4 plus 2, +6. So we have -1 squared plus 2. That gets me a 1 plus 2 is 3. 0 is going to get me a 0 plus 2 is 2. 1 squared is 1 plus 2 is 3. 2 squared is 4 plus 2 is 6. See the symmetry? -2, +6. -1, +3. 0, +2. 1, oops, that's a +1. 0, 1, +3. 2, +6. So my quadratic, oops, I missed my dot there, but there it is. You see how it's a smooth curve? Well, sort of bumpy, but do the best you can, make it a smooth curve. Does it a V shape? No, that's absolute value. So go ahead and try this one. Be careful of that negative. Pause it. Go ahead. Okay, let's try this. -2, -1, 0, 1, 2. Let's plug in -2. Now remember, -3 times -2 squared plus 1. That's like saying -3 times 4 plus 1. So -12 plus 1, -11. Same thing with -1. -3 times -1 squared plus 1. You can put that whole thing in your calculator, but make sure you use parentheses. So it's a +1 times -3 is a -3 plus 1, -2. Do the exact same thing, 0. Well, anything times 0 is 0, so plus 1 is 1. 1 times negative 3 is a negative 3, plus 1 is a negative 2. Hey, look at the symmetry. Negative 11 is my last one. Negative 2, negative 11, boop, right down there. Negative 1, negative 2, 0, 1, 1, negative 2, 2, negative 11. So this one points down. Excuse my bad curve there, but you get the idea. So there's my parabola. Point here being that parabolas can face down if they want to, if they need to. You'll find out why later on. Okay, as shown in the graphs of example 2, some parabolas open upward or downward. Just talking about that. Some open upward, some are open downward. Notice that the only difference between the two equations is the value of A. Let's jump back to that. A is our first term. So look how A is positive there, A is negative there. Notice the only difference is the value of A. Okay, so the A determines whether it opens up or down. So go ahead and write this down. A parabola opens upward when A is greater than 0. It opens downward when A is less than 0. So basically this, when A is positive, it opens up. When A is negative, it opens down. Okay. Think about this. I like to think about it this way. When A is positive, it's happy. It makes a smiley face. When A is negative, it's sad. It makes a frowny face. Pretty funny, right? So, determine whether it opens upward or downward. Now, is this in standard form? My answer is no. Here's what it looks like in standard form. Positive or negative? It's negative. It opens down. Pretty easy, right? Leading coefficient's negative. It opens down. Leading coefficient's positive. It opens up. Is that in standard form? Heck no. Add the 1/3 over to the other side. Positive or negative? Positive. It opens up. That in standard form? Yeah. Negative. It will open down. Okay. Now that doesn't tell us anything more about the graph. It's just, see how quick that was? Just that little piece of information told us a lot about the graph, whether it opens upward or whether it opens downward. Let's take a look here. Okay, well, another really important point is called the vertex of the parabola. Okay, the vertex of a parabola. The vertex of the parabola is basically that bottoming out point. Okay, it's the highest or lowest point. So go ahead and write that definition down. If a parabola opens downward, the vertex is the highest point. So like here, the vertex would be up there. If it opens upward, the parabola would be the lowest point. Okay, go ahead and write this down too. Actually, you know what? You don't need to write this part down, that minimum and maximum value. This is just another way to call that vertex point. The vertex is either a minimum or it is either a maximum. You just might hear that wording as a minimum or maximum value. If you say give the maximum value of the function, that means that point right there, that's the max value. And usually you're talking about the y value. If I say the lowest point, minimum value right there, that's going to be 0. That's going to be our y value of that point. So just another way to talk about it. So let's identify the vertex of the parabola and then tell what the minimum or maximum value is. So let's pick it off the graph. -1, -2, -3, +2. -3, +2. So you can say the vertex is at -3, -2, and that there is a minimum value because it's opening up. The minimum value is 2. Just take the y value right out of there. There's my answer. Quick and easy, right? Try that one on your own. Okay, so the vertex is at 2, 5. And now, since this one opens down, it's going to call it a maximum value, and the maximum value is 5. Again, just take your y value. There's my answer. Pretty simple. Okay. Let's talk about this last little part here. Now, domain and range. Remember, domain is x values, range is y values, right? Domain is x, range is going to be y values, right? So let's get this box out of here. Take a look at the quadratic function for the domain. I'm sorry. I forgot to have you write this down. You may assume that the domain of a quadratic function is all real numbers. That's something that's really important. The domain is always going to be all real numbers. The range will change depending upon, I just rhymed, the range will change depending upon the function. So do you notice here how I only have y values starting right here and on up? So that means that my y values are only going to be greater than 1. So I can say my range is greater than or equal to 1. Okay, everything above 1, y value is greater than or equal to 1. If it were to point down, then it would be less than that number. So take a look here. Find the domain and range. Domain, easiest one, all real numbers. Now my range, okay, so do you see how it points down? I want all values below that. Where is that line? Because again, for range, we only care about the y values. We only care about the up and down. -3. Y values less than or equal to -3. It's always going to be y greater than or equal to or less than or equal to, and then you take your y value out of your vertex. So try that one. Pause here and actually try both of these. So your domain, again, always all real numbers for both of them. I can go right ahead and do that for both of them. The range, well, they're both going to start with a y. But since this one points up, it's going to be greater than or equal to. So this one points down, it's going to be less than or equal to. Well, what is that point? -4? What is this point? 3. There we have it. Okay, so again, there's going to be another video, section 9.2 video. Watch that one. And then by Friday, you need to have both videos watched, notes taken, homework done.